Good morning to everybody. Today we have the pleasure of having here with us Luca De Guglielmo from Exeling. Welcome, Luca.
Hello, Michele. Thank you for this opportunity.
Exeling is a design house that has several years of experience in power electronics. Recently, with Exeling, we worked together on different projects like DC-DC converter for automotive application, Class D audio amplifier, wireless charger, and some magnetic design. Today, we will introduce our latest reference board developed by Exeling for Richardson RFPD and our partner. During this brief technical discussion, we will review few topics about GaN, including the importance of optimizing the gate drive loop, the role of negative bias, and the use of Kelvin source connection. We will also compare the results of SPICE simulation with real-world measurements. Next slide, thank you. Let me give you a quick introduction of our reference design board. Our reference design board features a typical half-bridge configuration using two 700 volts, 190 milliohms GaN devices from Innoscience, driven by a fully isolated gate driver from Skyworks. The isolation provided by the gate driver allows us to separate the power ground from the digital ground, ensuring optimal performance and reducing the risk of interference. The Skyworks driver offers exceptional noise immunity, and it can handle switching transition at speed up to 100 volts per nanosecond without compromising the signal integrity, making them ideal for GaN application. To power the gate driver, we picked the isolated DC-DC module from RECOM with a very low parasitic capacitance between input and output. The turn-on gate voltage is configurable to either 5 volts or 6 volts using a dip switch, while the turn-off voltage can be adjusted to 0 volts, -2 volts, or -3 volts, depending on specific requirement of your application. Now, back to Luca. Luca, why it's so important to minimize the driver loop with GaN power application?
Thanks for the question, Michele. As we know, compared to standard silicon MOSFET devices, GaN transistors have a lower threshold voltage and reduced capacitances, enabling them to switch much faster and with higher dividity than conventional silicon devices. However, high dividity leads to high capacitive currents flowing through the gate drive loop, as shown by the red dotted trace on this slide. This creates a spike on the gate source voltage, which may cause forced turn-on during the off time of the device. Here are the results of a simulation during a positive dividity transition. The drain gate capacitive current, shown before, creates a voltage spike of about 1 volt across the gate source voltage. However, due to the internal gate resistance, the internal gate source voltage is higher than what you can see on the gate pin. What I want to highlight is that even if you don't see a large spike between the gate and source pins, you may still have some degree of cross conduction between the high side and the low side transistor, because internally to the device, even if only for a short time, you may have exceeded the threshold. This is why it's always advisable to consider a negative bias voltage to switch off the GaN, in addition to implement a low impedance gate loop path. Here I'll show you how we optimized the gate loop in the layout on our demo board. As you can see, we kept the turn on and turn off paths as short as possible, and also minimizing the areas formed by the entire loops. What is important to keep in mind is that in addition to placing the bypass capacitor as close as possible to the driver, their orientation is also important to minimize the gate current path. Just to show you on a real board the impact of the gate loop layout, I captured some data using the oscilloscope. The top trace shows the switching node, and the bottom trace shows the gate of the low side GaN transistor. On the switching node, we have a dividity of about 50 volt per nanoseconds and a spike of 1.28 volts with the current layout. For comparison, I added a jumper wire to increase the loop length by about 1 centimeter to emulate a bad gate layout. With the increased gate loop, the peak voltage rises to 2.25 volts, almost double. But in both cases, a negative bias voltage is advisable. Generally, for high voltage GaN devices, for example, in half-bridge configuration above 300 volts, I prefer a negative bias configuration around -2, -3 volts.
Thank you, Luca. Is there a way to predict or simulate the voltage spike and assess the risk of cross-conduction event prior to finalizing the PCB design?
Yes, some papers suggest simplified formulas to calculate the spikes based on simplified models. However, you can run a quick spike simulation before starting the layout of the final board, using the models provided by the manufacturers, and accounting for the parasitics by adding inductances of few nanohenries. Here I am showing the comparison between the two cases described earlier. As you can see, in this case, there is a good match between the simulation and the real-world measurement. But there are many uncertainties to consider, so don't expect to always get accurate results, as I'm showing here. However, even in simulation, you can observe the impact of a longer gate loop path on the false turn-on risk.
Very nice, Luca. What about the Kelvin source?
Let me show you a quick comparison of 3 different ground return paths on our demo board. The first case is what we have implemented on the board, where the gate return path is through the dedicated Kelvin source pin of our Innoscience GaN. In the test in the middle, just for comparison purpose, I disconnected the Kelvin source and used the power source pin of the GaN. And on the bottom, I don't even use the dedicated gate return path and just going through the power ground plane. You can see that the dedicated Kelvin source helps minimize voltage spike. But if Kelvin source pin is not available, just make sure to keep the two ground loops separated to mitigate the spike, as I'm showing in the middle. When instead the ground return path is shared with the power ground, the voltage spike is much worse. Furthermore, in this particular case that I'm showing at the bottom, the negative spike exceeds the -4 volts, risking going beyond the device maximum ratings. In other words, Kelvin source is very effective in reducing parasitic inductance in the loop, and so the voltage spike.
Thank you, Luca, for the excellent presentation and for sharing with us your experience with GaN technology. At Richardson RFPD, we have several initiatives focused on wideband gap devices, And Luca from Exeling is one of our key resources when working with GaN devices. Exeling is a design house that provides technical consulting service in power electronics field. In collaboration with IPERA and Exeling, a spin-off of the University of Salerno, we are also promoting dedicated courses and workshops on GaN technology. If you are interested, do not hesitate to contact us and stay tuned for upcoming webinar and initiative from Richardson RFPD.